Hello, everyone. In this video, I'll be going over problem 13 in chapter 12 of the Fundamentals of Mass and Heat Transfer textbook. So this problem describes a burner stove top with a dark surface that can be approximated as a black body. The, the burner has a diameter of 200 millimeters. The stove top operates at a uniform temperature of 250 degrees C with the ambient air at 20 degrees C. Without a pot or a pan burner, we want to find the rates of heat loss by radiation and convection with a 90% efficiency of heat transfer assumed. What is the electric power requirement? And at what wavelength is the spectral emission a maximum? And then we want to plot that from a range of 100 to 300 degrees C. So if you'll look to my solution, I started with a quick sketch, just recreating the the schematic given. I defined all the variables and evaluating at about 400 Kelvin just above the surface of the burner. It will be quite hot, but not quite 250 for the air. Uh, Using table A4, I got some properties for the air. This will be important for determining uh, the convection coefficient. So first things first, this is a radiation. This is a radiation problem, so we're going to find the heat loss rate due to radiation first. So energy flow of radiation is equal to the area times the emissivity times the Stephen-Boltzmann constant times the temperature of the emitter to the power of 4. Since we are taking this to the power of 4, we do need it in Kelvin instead of Celsius. Now, this is going to look very similar to radiation heat flow when you got a small object, large enclosure, but since instead of receiving, this is emitting the radiation, we neglect the surrounding temperature. We just care about the energy that is leaving the stovetop. Area in this instance, since it is circular, it's just pi r squared or 1/4 pi d squared. Since this is black body, emissivity is equal to 1, and 250 degrees C is equal to 523 Kelvin. Plugging all this into the equation, we get a heat flow out of the stovetop due to radiation of 133 watts. Now, the radi now for So now in order to find heat loss due to convection, we need to find the convection coefficient. So we're gonna have to go through a bunch of that stuff. First things first, we're gonna need the characteristic equation, the characteristic length, which is the surface area over the perimeter in this instance, which is just gonna be d over 4 since it's a short cylinder, which is just gonna be equal to 0.05. Then we're gonna wanna find the Rayleigh number, which is equal to G times the thermal expansion coefficient, which is just equal to 1 over the density times the density at T infinity minus the density of T infinity minus the hot density over the change in T, which is just going to be using the surrounding temperature and the max temperature. This will give us a value of 0.00245 over Kelvin. You can find all the values necessary to compute beta in table A4 if you know the temperatures. Uh, then you're going to multiply all that by the change in temperature times the characteristic length cubed, all over dynamic viscosity and thermal diffusivity. Once again, these values can be obtained from table A4, which gives a Rayleigh number of 6.35 times 10 to the 5 power. So now in order to find H, we need to know KL. In order to find H is just equal to the thermal conductivity coefficient over the characteristic length times the Nusselt number. Now, in this case, the Nusselt number is going to be equal to 0.45 times the Rayleigh number to the 1/4 power. This is obtained from equation 930, which details convection in the instance of the far side of a heat plate. Plugging all those values in, we'll get a value of H of 10.5 watts per meter squared Kelvin. Then we can just plug this into the standard convection equation, H times A times delta T, and get a total of 75.7 watts. Now, knowing this, we know that if we add the convection loss with the radiation loss, we get the total loss. And knowing that there is a 90% transmission rate, we know that the total power times 0.9 is equal to this additive value, which means that at 250 degrees Celsius, we have a power requirement of 232 watts. Then for the next part, we plug the temperature 250 into the Wien's law equation, pretty much the emission spectrum maximum times the temperature is equal to the constant C3, which is equal to 2898 micrometers Kelvin, which will give us a maximum emission spectrum of 5.5 micrometers. Now, if we look at the table, I didn't find the exact values, because all that you'll have to do is, instead of using 250 in all these previous equations, you just plug in like 100 or 350 to know the range. In general, we do know enough to sketch the relationship between all the powers. For example, as we calculated, radiation is where we're losing the most heat in this instance, which makes sense because in order to calculate that, we're using temperature to the power of 4, which means that when temperature increases, it will increase at a much greater rate than that of convection. So convection is the lowest, radiation is the highest, and of course, the power on the other side of the equation is going to be even greater than all that, because if you add the radiation, the convection heat losses together, it is only 0.9 P, or 90% of the energy that the heater is putting into the stovetop, which creates a graph that will look something to the degree of this. So that's all for this video. I hope that it was very helpful, and I hope that other videos on this channel will serve you well in the adventure that is mass and heat transfer.